Starting off our wonderful season for Astronomy, we have Macy Huston. So Macy Huston is a postdoctoral scholar at UC Berkeley, working in the Moving Universe lab with Professor Jessica Liu. Their research focuses is stellar mass black holes using both telescope observations and computer simulations. They received a BS in engineering physics from Ohio State in 2018 and a PhD in astronomy and astrophysics from Penn State in 2023. We are so pleased to have Macy here, so please come on up and take it away.
I'm so excited to be the first person presenting this Astronaut season, especially because earlier in the season the sun sets earlier and I don't have to stay out as late. So I'll start with just a definition of what a black hole is. So a black hole is a singularity. That means that there is some amount of mass that exists just in a single point in space. It has no physical size. And so that's what we call a singularity. And then you may have heard of black holes' size being defined by an event horizon. So the event horizon isn't really like the size of space that it takes up, but the event horizon is the distance away from the singularity where nothing can escape the gravitational pull of the singularity. So at that point, the illustration is showing like a person shining a flashlight and none of that light is able to escape past the event horizon. It all gets pulled back in towards the singularity. And then when you're beyond the event horizon, the black hole is still able to have some effect and bend light, but it won't completely prevent it from moving on out into space. So that's what a black hole is. I'll also mention if anyone has like clarifying questions as I'm talking, feel free to raise your hand. And then we'll also have time for kind of more expansive questions at the end too. So how do black holes form? This is kind of the simplest picture that we think about when we think about how stars turn into black holes. So the lower mass stars in the universe, like the sun and stars less massive than it, generally are going to very slowly over time burn through their supply of hydrogen. They'll expand and cool into a red dwarf star and eventually either explode or just gradually cool and form a white dwarf, which is a compact, dim object where fusion is no longer happening. When you move on to slightly larger stars, a few times the mass of the sun, we often think of these stars as going through, a similar evolutionary process, and then they may experience a supernova where they explode and then leave behind a neutron star. A neutron star is a very dense object, denser than a white dwarf. It's the densest thing out there other than black holes. And this is the end product of stellar evolution for some of these large stars. But then when you go on to look at the very largest star, we think that most of these evolve, turn into red giants, explode in a supernova, and then leave behind a black hole. However, it's actually a bit more complicated than that. Unfortunately, this does not explain all of stellar evolution. My job would be too easy if it was. So this is a bit of a more complete, but not fully complete picture of what stellar evolution looks like. So a protostar is just when a star is beginning to form, and then starts to burn hydrogen and go through its main sequence lifetime. And then after that, when stars run out of fuel, they kind of grow and expand. They go through a lot of kind of different dramatic events that can happen depending on exactly what's happening to that particular star. So when you're looking at the kind of the higher mass stars that we can think of as stars that might form black holes, there's a number of different routes that these can take in their evolution. So some of these will go through supernovae. They will explode. Some of the outer layers of the star will be kind of shot off into space. Yeah.
What makes a white dwarf glow?
Just heat, residual heat. Yeah, it's not creating any more energy through fusion, but it just has some remaining heat. Yeah.
Will these white dwarfs continue to burn forever, or will they eventually die out too?
They're just going to very, very gradually cool over time. So they'll have just lower and lower temperatures.
But what happens when they finish cooling?
They just sit there.
Like a mass of stuff in space, like just heavy metal?
Yeah, it just kind of sits there and then, yeah, can't really see them from any source of their own light at that point.
Well, it's not heavy metal. It's
Core.
They're usually like carbon, nitrogen, and oxygen, typically is the main content of the white dwarf. Yeah, so for these higher mass stars, after they go through supernovae, a lot of the outer layers and mass will be blown off into space, and they'll leave behind a single dense object like a neutron star or a black hole.
Louder, please.
Louder? Okay. Yeah, so there's a couple of other things that can happen as well, instead of just going through a supernova and turning straight into a black hole or neutron star. You might have a star that actually just directly collapses from the giant phase into a black hole with no explosion, no supernova, no dramatic event that we might detect. There's just a star. And then one day it collapses into a black hole that we can't see anymore. So there are projects that look for stars that have just disappeared to try to find this kind of thing. And I know there's a couple of kind of candidates out there, but we don't actually have any confirmation for certain that this happens. But theoretically, we think it could. And then the last example of an evolutionary path is a really large star that could potentially undergo a supernova, but all of the material gets blasted off in the explosion, and there's nothing left behind. There might be massive stars that don't leave any black hole or neutron star or anything behind. Yeah.
Does this account for, do these notions of evolution account for primordial black holes?
So primordial black holes do not come from stars, and I will talk about them in a minute. Yeah. Okay, so this is generally how some of the time from stellar evolution we get black holes. So these are stellar mass black holes. Yeah, question.
Do the stars spin? Is there any rotation involved in this formation of a black hole?
Yeah, stars generally spin. Black holes can spin too.
As well, then.
Yeah. And so then, in addition to us having black holes around that have just kind of formed from a single star and exist there where the star used to, there are also supermassive black holes. These are black holes that are millions to billions of times the mass of the sun that lie at the center of most galaxies, including ours. And so this is an image of one that was taken pretty recently. The Event Horizon Telescope has taken a few images, and this is radio wavelengths. This isn't truly what you would see in visible light. This is what you would see in radio of supermassive black holes at the centers of galaxies. And we don't actually know for sure how supermassive black holes form, but we think maybe it's from, gradually a bunch of mergers over time of smaller black holes, and then some other ways that matter can kind of just gravitationally pull together in early stages of a galaxy's evolution. And then the third type of black hole I wanted to mention is primordial black holes. So primordial black holes are a purely theoretical idea. We have no confirmation on whether these really exist or not. But the idea here is that shortly after the Big Bang, before any stars or galaxies started to form, there may have been some sort of dense patches that formed in the early matter of the universe that has collapsed and formed black holes directly that never went through any phase of being a star or stellar evolution, but just immediately these may have formed into primordial black holes. And one of the reasons we think this might exist is that we know there's something out there that we call dark matter. Because when we look at the speed that stars move through their galaxies in, including in our own galaxy, we know that there's some matter that exists that we can't see. There's got to be a bunch of matter out there in these galaxies that we're not seeing in the luminosity of stars. There's got to be some dark particle or large objects out there that explain this matter. So one of the possible explanations for this is a hidden population of black holes that we just can't see because they're dark. And so there have been a lot of studies using the technique I'm going to talk more about in a minute to try to find these primordial black holes. And so far, we haven't been able to confirm or rule them out, really. So it's an interesting theory that we're still trying to test. And so that brings us to, how do we find black holes? As we mentioned, black holes are dark objects. They don't inherently by themselves emit anything that we would be able to detect. So there's a few different things that we can do to actually detect them. And basically, we have to do this through their interactions with other objects. So one of the ways that we can do this is by studying black hole accretion. So this is radiation that will be emitted from a gas disk that surrounds a black hole. One way that this can happen is if a black hole and a star are orbiting each other in a binary system. If the star in that system is like a red giant or something that gets puffed up, there might be some outer material that starts to be pulled off of the star and start to slowly orbit the black hole and gradually fall into it. So this can cause that gas to heat up and create a detectable signature that we can observe to detect black holes. And then we have a kind of slightly less dramatic interaction that black holes can have with another star. If there's a star and a black hole that are in orbit with each other, they're not necessarily have to be interacting in exchange of material or anything. But if we can just observe that star in an orbit and figure out that there must be a massive object there, but we don't see a star, if you're able to set a limit on how bright that object would have to be, if it was a star, you can rule out a star and confirm that you have a black hole. So this is another way that we can find invisible black holes by their gravity pulling on objects around them. So this is an example here of a system like this that was recently discovered with the Gaia telescope of a star orbiting a black hole.
But what if it's a neutron star? You wouldn't be able to see that anyway either, right?
Yeah, if you can measure the mass, you can figure out that it's too massive to be a neutron star. But we could also find neutron stars that way. And neutron stars sometimes are detectable in their radio emission too. The third method that we can use to find black holes is gravitational waves. So when a black hole merges with another black hole or a neutron star, these objects will spiral in and lose some of their angular momentum in their orbits to gravitational waves. And so these waves will just fly off into space, and we can use technology like the LIGO. I'm forgetting what that's, laser interferometric interferometer, gravitational wave observatory. So these interferometers basically just, we have them existing on Earth, and they measure the size of space. And you can basically see the size of space changing as gravitational waves move through it. So we can use this to detect dramatic merging events that result in shooting off a lot of gravitational waves from black hole or neutron star mergers.
Those are relatively new, right?
Yes.
And are they directional? Are we able to measure the direction that those gravitational waves are coming from to find the black hole?
Yeah, if you're measuring space in multiple dimensions, you can get some measurement of the direction. It's usually not super precise that we can measure the direction, but we can put some limits on it. And then sometimes people will follow those up with like optical telescopes to see if you can see an optical counterpart to the gravitational wave event, but that's not always successful. And then the third method for finding black holes, which is the one that I work on, is gravitational microlensing. So this is another way that we detect black holes by their effects on other objects. And in this method in particular, it doesn't require any other star or anything to be in the black hole's orbit. The black hole just has to happen to pass in front of some other star in our galaxy or anywhere else and bend that background star's light towards us, causing the star to appear brighter and to move. So hopefully my animation plays right. So this is an animation where we're looking top down in the galaxy. So we've got us here on Earth. And then we've got a background star out in the galaxy that we can look at. And so its light is shining out towards us. And if there's a massive object here in between us and that bright object, the massive object can act as a lens and pull that light towards us. So in this example back here, this is just any star anywhere in the Milky Way that we can monitor. And then, so the only requirement for this object is that it has to be bright enough for us to see. So stars. This lens object can be any object that has mass. A star can lens another star. You can also see this for planets, neutron stars, black holes, white dwarfs, any object with mass that moves through our galaxy. And then we are here on Earth receiving this bent light from the source star. So we're going to call this object that we're monitoring back here, that is our light source, the source. And then our intervening object that bends the light is what we call the lens. Yeah.
Backing up a little bit. So how black can a black hole be, since there are potentially vacuum fluctuations that could sort of give a background annihilation rate?
I don't have numbers for you on that.
At all detectable.
Not often. Yeah. Yeah, that's the kind of thing that's really tough to do.
So that's for the instrumentalists.
Yes. Okay, so and this is just a different view of the same kind of type of microlensing event. And I'll play this multiple times since there's a lot going on here. But what we're looking at here is that we have our lens object, which is a black hole in this animation, and we're watching our background bright source star move behind it. So as the object passes behind the lens, you can see that, whoop. Sorry, animations are hard. The background star is going to produce these two weird warped images that move around a ring around the lens. And so we call this ring the Einstein ring. It's just kind of a physical size on the sky of the ring around the lens. That's just a function of its mass and the distance between these objects. And so what happens physically is that the image of the star gets warped as the lens passes in front of it. However, our telescopes are not good enough right now to actually make out the shapes of these different images that form. We can't actually observe it like this in space today. What we can see instead is two different effects on the object. So one of these is a change in brightness. You can see these images become larger than the star originally was. So that makes the star appear brighter than it normally is. And in addition, you can see that the images move in the weird path around the Einstein ring. And so we also see that as the star appearing to very, very slightly shift in position on the sky. It's an extremely small effect. And most of our telescopes can't observe that positional shift, but as I'll talk about, we have a few that can. All right, so to get a little bit more into the details, this animation is showing basically the same thing as the last one. You've got the lens here, and then it's Einstein ring around it in green, and then the images produced in blue, and the true position of the source star is in red. So the source star really does go behind the Einstein ring, but all we're able to see are these blue images. And so as I mentioned, as these images become larger, we can see that it increases in brightness. So just proportional to how the size of the image is increasing, the apparent brightness that we see of the source star is going to increase. So this is one of the signatures. This is the main thing we look for when we're searching for microlensing events. We call it a light curve, where you're just monitoring the brightness of the star over time, and you see it change due to the lensing. And these events often happen on the timescale of like months for a star lensing another star. If you have a more massive lens like a black hole, it'll be a couple hundred days typically. Yep.
Why does that second image appear?
Yeah, so in gravitational lensing, you get two images. The larger one, which goes on the outside of the ring, we call the major image, and then this one we call the minor image. And yeah, so that's the shape that gravitational lensing makes. And the exact shape that it turns out and how these are aligned depends on exactly how close the lens and source star pass within each other. So actually, if a lens and source star were to be perfectly aligned, you would actually see the Einstein ring lit up perfectly as a ring. But when they're offset a little bit, and in reality, they're always going to be offset at least a tiny bit from each other, that's when you get these separate major and minor images. So this changing in brightness that we see in microlensing is what we call photometric microlensing, just indicating that it's a change in brightness.
I'm still puzzling over that because the luminosity of the star obviously is not changing. So is this a function of it's curving space-time and concentrating the amount of photons that we're seeing visually, or what exactly is, I mean, I hear you say it's larger, so it appears brighter. I mean, but are we actually seeing more photons, I guess, as that occurs?
Yeah, it bends the path of light from the source star and pulls more of them towards
Okay,
us.
so it really does concentrate.
So that means that more light would shoot out past us, but it kind of pulls it all more towards we see more of it.
Yeah.
So this photometric, you say, and with a geometric argument, I'm assuming is there any coherence between those two images or similar polarizations that you could extract a bit more information from other than just the energy? Spectrally?
Spectrally, you could. So so gravitational lensing is like it doesn't change based on the wavelength of light. So if you're magnifying the spectrum of a star, it magnifies all parts of the spectrum equally. So this will happen equally at radio wavelengths, visual wavelengths, and all of that. Yeah.
So there's no extra information.
Yeah, not necessarily. There's always more complicated things that can happen. You can have, multiple lenses, multiple sources, and you might have some additional information about the lenses and sources from other observations that you can use to learn more. But microlensing at its core, inherently, you don't necessarily get more from that. So then the other signature that we talked about, we briefly mentioned the position of the star will appear to shift on the sky. So this one is a little more complicated. This is what we call astrometric microlensing. This animation we're looking at up here is a little bit different because it locks the source into a stationary position, and we're instead looking at the lens moving across it. But it's the same setup. We have a lens star, its Einstein ring around it. We're seeing the source star in the empty circle here, and then we're seeing the images produced in blue around there. And the new thing that we're seeing here is the red filled circle. So this is basically kind of the average position of the two blue images, but skewing more towards the brighter image. And this is what we see as the apparent total position of that object that we're not able to resolve the separate images of. So when we kind of put this in like a scientific plot, let's say we're measuring the position of the source star over time. We're going to see it follow a weird little looping path on the sky, according to what that red filled circle is doing. So this is really, really tiny on the sky, the astrometric microlensing effect. And so microlensing events happen when you get the chance passing of some lens object in front of some source object. We don't typically know when this is going to happen. If you're looking towards the center of our galaxy at any given time, you would expect that roughly one star out of a million happens to be being microlensed in that moment, just based on how many stars are out there and what speeds they're moving at. And so we need to monitor a large number of stars in the Milky Way and then just happen to pick up these chance events when they happen. So we usually do this with optical or infrared telescopes. Optical telescopes are what we primarily use here on Earth, because our atmosphere is translucent to optical light, and optical instruments are generally, relative to infrared, optical instruments are easier, cheaper to build, typically. And then infrared truly is the ideal way to search for microlensing events, because as you can see in these two different images, when we're looking at optical light, dust is really a problem in the plane of the Milky Way and blocks out a lot of stars from our view. When you're looking at infrared light, you can see through that dust because infrared light doesn't get absorbed by dust as much as visible light does. So infrared is a really exciting way to do microlensing science, but optical is a lot easier, so we do some of both. And so as an example of one of the existing microlensing surveys, this is going to be some results from the optical gravitational lensing experiment. This is a project led by a group in Poland that surveys the sky every night in these different regions So all of the little blue and white shapes are outlines of their telescope's field of view. And these are all the patches of sky that they look at either every night or every few nights. They kind of prioritize the central galaxy a little more than further out. So this is what the Ogle survey looks at in our galaxy. And all of the yellow dots around are microlensing events and their location in the galaxy for events that were detected in the 2024 season. So in 2024, the Ogle survey detected about 1,400 microlensing events. And so, as I mentioned before, microlensing events can be caused by anything, any massive object acting as a lens. It can be planets, stars, neutron stars, black holes, anything. And based on simulations, we think that roughly 1% of the microlensing events that we see towards the center of the galaxy would be caused by black holes. So photometric microlensing surveys provide us those light curves where we can see the brightening of the stars. They're usually not high enough resolution to provide the astrometry we need to measure those tiny shifts. So what we do is look through these photometric surveys and pick the most interesting events to try to follow up and measure astrometry and figure out to get a precise measurement of the mass of the lens object and determine whether it's a black hole.
How long do they last?
Black hole microlensing events generally last like a couple hundred days. So we have time to like notice the stars are getting brighter and select them for follow-up, but you gotta be paying attention as the alerts are coming out for new events. Yeah.
The microlensing, can you then just trace where it was moving and see more events? More microlensing happening in the path of the black hole?
The lens would have to be moving pretty fast to get to another star in a reasonable amount of time. This is something that has happened maybe once or twice. I think there's been like a white dwarf that's pretty close to us, so it seems to be moving pretty fast on the sky. And we have a few predicted microlensing events coming up in the future from that, but it's generally a pretty small number that we can predict just because we don't have the motions of that many stars measured that precisely. But yes, we can predict them occasionally.
Just a quick reminder, please raise your hand before you ask questions so that our speaker can call on you.
Oh, I've been calling people. Yeah, so we use these photometric microlensing surveys to pick out our best black hole candidates to follow up. So there's a couple of things that we look for when we try to pick our best events to follow up and search for black holes. The main thing is we're looking for microlensing events that show evidence of a high mass lens, because the majority of microlensing events are going to be caused by lower mass objects, typically stars. And the majority of stars have masses lower than the sun. So these are generally pretty low mass objects. But when we're looking for black holes, there are a couple of parameters that we can measure from light curves to pick out the good candidates. So this is one example of a microlensing light curve. The pink line is like what we showed before, the track of what brightness should look like for a microlensing event. And the black dots are all the times that we actually got data from the Ogle telescope. So these are the actual measurements made. And then we calculate our best fit line in pink to describe that event mathematically. And so from that calculation, there are two parameters that we can try to measure. I won't get into too much detail on these, but one of the main things we've already mentioned is timescale. How long does this brightening event happen? These events will last longer for higher mass lenses, so we look for long events. The other parameter here is microlensing parallax. It's a bit complicated, but the thing to know about that is that lower microlensing parallax is indicative of a higher mass. So we want to look for events that have long timescales and low parallaxes. And so we're showing in here a simulation of some different simulated microlensing events on this axis. And you can see that black holes and the black dots here live on a pretty separate part of this plot from stars, white dwarfs, and neutron stars. So when you're looking at these two measurements, it's pretty easy, for the most part, to pick out which microlensing events should be black holes. So we try to find those rare 1% of events that fall into this space and get higher resolution astrometric imaging on as many of those as we can. And so this is an example of a few targets that have been looked at, some by our group here at Berkeley and some by other people. The pink one here actually corresponds to this event. This was a very long time scale event, but it actually ended up having a little bit of a high parallax. So it's kind of an odd event over here. And we'll talk a little bit more about that one in a minute, but that is an extremely interesting microlensing event. And then we've got a few other ones in circles here that we have either that we have followed up and are still working on some of these newer ones. And then we've got a few other events that were covered by earlier programs seeking to do this that weren't really accounting for microlensing parallax at the time. Pretty early on into the field of this science, candidates were just selected for long time scales. So the success rate wasn't as high as it could have been for finding black holes. And so we're making more of an effort now to take microlensing parallax into account and get better candidate selection. So once we have these candidates, we want to follow them up to get astrometric imaging to measure that positional shift and actually get a precise measurement of the mass of the lens. So there's only really 3 instruments around today that can do this. So we can use the Hubble Space Telescope, and the Hubble Space Telescope has been used to confirm a black hole before. I'll talk a little bit more about that one in a minute. You can also use JWST, the James Webb Space Telescope that just launched a few years ago. I have some imaging started on a target with this one, but we haven't covered it for a long enough time to know whether we're getting a good astrometric shift on that one yet. And then our group, for a long time, Professor Jessica Liu, who leads our group here at Berkeley, was one of the kind of founders of this field. And she started doing this years ago with the Keck telescopes that she also builds instruments for. And so this is a program that we've been continuing from her work over the years, where we do this imaging from the ground, but there's a lot of extra technology going on here in the Keck telescopes to give the astrometric precision we need. So we actually use lasers. We shoot lasers into the atmosphere, and then the contents of the atmosphere are going to reflect some amount of that light back down at us. And we can use that to measure the turbulence in the atmosphere, because our atmosphere is going to warp any light that comes through it to our telescopes. But if we can measure that warping that's going on, we can account for it and much more precisely measure the positions of stars than you typically can if you're not accounting for the atmosphere. So this is why only telescopes with this adaptive optics technology can do this from the ground. Otherwise, you can just do this from space and not have to deal with the atmosphere. And that's pretty cool, but it's really hard to get time on these telescopes. And we also here at UC work on developing instruments for the Keck telescopes and use these to do this science a lot. So we use both. And a lot of the history in our group on this project involves the Keck telescopes. And so, so far, we have only confirmed we only have one confirmed discovery of a stellar mass black hole by itself. All of the other black holes that we know about in the Milky Way come from detecting their companions in binary systems using one of those other methods I mentioned before. But using microlensing is the only way to find a black hole that doesn't have anything in its orbit, an isolated black hole. And so this was the first discovery of one that was just made a few years ago. So this is also the name of this event. You'll see these names with a lot of letters and a lot of numbers floating around a lot. So I'll just say what it's for. OGLE is the name of the experiment that found it, the optical gravitational lensing experiment. It was identified in the year 2011. It was detected in the area of the galactic bulge. That's a region towards the center of our galaxy. And 0462 means it was the 462nd microlensing event detected by that program in that year. So that's what all these letters and numbers you see are for. Whenever you see astronomical objects with names like that, for microlensing events, this is the standard. Sometimes other types of things have different reasons for all those letters and numbers. But this image here, so this is a few different images during and after the microlensing event in question. So you can actually see, this is really cool. The arrow is pointing to the star in question here that was being lensed. And you can actually see that it's brighter during the lensing event and then dimmer out here later after the lens has moved off of it. So this was a really neat microlensing event. And this was initially detected by the photometric survey OGLE, like we mentioned. Yeah, was there a question?
How do you know that it's not some sort of like supernova, or how do you know that it's not some other reason?
The shape of the light curve. It'll increase and then it'll go back down. And then long before and after the microlensing event, it'll be flat. So observing these events before and after as well to confirm that they were flat before, they're not like some flaring star, is also important. And the shape of a microlensing event is pretty distinct. So if you can monitor it long enough, and if you can get enough observations to characterize that light curve well, you can clearly determine when things are microlensing. And so this event was initially detected photometrically with OGLE, and then it was followed up with the Hubble Space Telescope. So this image here is just showing the position. This is the on-sky apparent path of the source star. And this is just kind of separating out the two dimensions versus time. So you can see the star follow this weird little path characteristic of an astrometric microlensing event. And by measuring the size of that shift, they were able to confirm that this was a lens mass 6 times the mass of the sun. And then when we get that mass measurement, technically that lens could be a star that is 6 solar masses. Stars exist that massive, but we can figure out that it is a black hole for sure if we when we're looking at that area of space, we know how bright a star of that mass would have to be. And if you don't detect the luminosity of that star, you can rule out a star and confirm it's a black hole. Yeah.
What's that unit of time? I've never seen it before.
Modified Julian date. It's just days, where 0 is some weirdly specific date. Yeah. So this discovery was made by our group here at Berkeley, but before I got here, I can't take credit for it. This was work done by Casey Lamb, who was a grad student here at the time, who's since graduated, and Jessica Liu, who's the professor who leads our group. Yeah.
How do you initially say that an event is going on? Like, do you take a broad image of the sky, then you do some machine learning on?
Yeah, we monitor a large number of stars and see how their brightnesses change over time. Machine learning has been adopted pretty recently to try to do this. Before that, people would they would set the computer to search through the light curves and then pick out ones where 3 consecutive points were increasing in brightness above some threshold. And then someone would usually physically have to go through by eye on all of those and figure out which ones look like real microlensing events. That's pretty tough. And with bigger and bigger surveys, it's becoming harder and harder. So a lot of people are working on using machine learning now to try to do that more efficiently. But yeah, traditionally, there was a lot of by eye analysis in this field, which is a lot of work. And so I wanted to highlight a few different things that our group here at Berkeley is doing to try to improve our ability to find and study these black holes. So in particular, a project that I'm working on is LS4, the Lucia-Schmidt Southern Survey. This is a new survey that's going to study a broad region of the galactic plane, observing it once per night through basically March through October each year for the next about 5 years. And that's going to start operating a little later this summer. So we're very excited about LS4. This is going to be a photometric survey where we can pick out candidates that we can then follow up with other instruments. LS4 itself doesn't have the precision to do the astrometry, but it'll be able to monitor a larger number of stars than a lot of surveys because it has a very large field of view. So we're very excited for that. It's located in the southern hemisphere, so it has a better view of the galactic center than we would up here north. So this is going to be a really great survey for identifying photometric microlensing.
You might be getting this. I'm just wondering what the purpose of this is. I mean, granted, this is the only black hole you've found. It's not, sort of interacting with a companion. So in that sense, it's unique. So what, though, right? At the end of the day, what are you learning? I mean, what do you hope to gain by? You're getting there, I'm sure.
Yeah, so this is very early on in this field. We only have one so far, but we're trying to build up a population to detect a bunch of them and measure their masses. And then by measuring the masses of isolated black holes and also comparing that with black holes that have a companion, we're hoping we can kind of learn more about how these objects form and learn more about how stellar evolution works and what end products it produces, what kind of masses do black holes typically form at. And microlensing is the only way to really study these isolated black holes in this way. So it's the main motivation. I think Becky was first.
So the center of the galaxy has supermassive black holes. Would this technique be useful to measure those?
Yeah, so the center of the galaxy has the supermassive black hole. Gravitational lensing from that would be kind of a different scale than microlensing. But there are also theories about intermediate mass black holes, because we talk about stellar mass black holes and we talk about supermassive black holes. That's like a few times the mass of the sun up to millions of billions of times the mass of the sun. There's got to be something in between, right? And there's some theoretical reasons that we think those might exist more commonly at the center of the galaxy. But the weird thing about those really high mass objects is that microlensing events would last a really long time, and you might not notice that the brightness of the stars they're lensing are changing because it's so slow. So if we get some surveys ongoing for a really, really long time, hopefully we can start to do some of that science, but it's pretty tough.
How do we know, or can we figure out the size of the supermassive black holes at the center?
That's so that's not really my field. But there are ways to measure it, not through microlensing. Yeah.
So if the microlensing event lasts 6 or 8 months or something like that, and how long is your exposure time when you're using one of these telescopes? You're not going to get beam time on James Webb Telescope for a year.
Oh no, so our exposure time will be like, an hour or two, and we'll try to do that a few times a year. So when we're proposing for time on James Webb, we're proposing for like a few hours a year per event we're looking at. And then we'll want to do it for several years though, because the astrometric signal kind of lingers longer than the photometric signal does. So to get a good measurement of it, we often want to monitor these things for like 4 to 5 years, measuring its position 2 to 4 times a year, depending on the exact details of that particular event. Okay.
Are you able to determine how far away a black hole is that you find from microlensing?
Yeah, if you can detect both the photometric and astrometric signals, you can calculate that. Yep. Yeah.
Again, just think about these things working on their own. Most stars are in binary or multiple star systems, right? And oftentimes that's what these black holes will interact with. Are you hypothesizing that these things, when you find them, are more likely not going to be part of binary star systems, or?
Yeah, so this is something we're trying to find out, but we think that the majority of black holes are probably isolated, because when black holes form, they go through a very explosive supernova process, and we think that that would disrupt binary orbits most of the time.
Okay.
So we think most of them are probably isolated, but we can also detect binary black holes, like a black hole system through microlensing, and we've got actually a candidate system we're studying right now that looks like that, but we don't know for sure yet. Yeah.
Just like broadly speaking, like how much more of the sky are we like monitoring now versus like 5 years ago or like 20 years ago? Beginning of grad school. Is it a crazy bigger amount of observation going on, or?
Honestly, in the last 5 years, I don't know that it would have grown a ton. But we've got some great projects in the future that are going to grow it a lot in the next couple of years. Including the Rubin Observatory project that's supposed to start later this year. That's going to monitor the whole southern sky all the time. And so we're going to get a lot more events detected from that, and projects like LS4 in the near future. Yep.
Some people theorize that there are a lot of primordial black holes that are much smaller, not the large ones that have come from the explosions of supernovae Do you think that could be true?
Yeah, we're not able to rule that out. We are very hopeful that with microlensing, we can try to narrow that down more in the future, but it's also hard when you're looking at low mass objects. Those objects won't be bright inherently on their own. If you're looking at like a free floating planet, it's not going to be luminous enough to detect. So it's hard to know if you measure the mass of an object like that, whether it could be a primordial black hole or just a dark object like a planet. So it's going to take a lot of measurements over time and kind of bringing those together with what we know about planets from other sources, to try to figure out if this population of objects that we're seeing is just free floating planets or primordial black holes. It's tough to disentangle.
So related to dark matter, the black holes would then have to be pretty evenly spaced, or at least proportionally spaced to the matter that we are able to see, and so they would have to be relatively small if we're talking about throughout the galaxy.
Yeah, I mean, theoretically, they could be, you know, stellar mass black hole size down to like asteroid masses. And then in terms of the nature of dark matter, with what we can determine from the velocities of stars through the galaxy, we know that kind of the density, the distribution of dark matter in the galaxy is a lot more spread out. There's kind of like a big, broad halo that would have a bunch of this matter in it that goes way beyond where most stars are. So you can try, you know, looking out in weird parts of the galaxy and see if you see a bunch of dark objects, and that's another way to try to search for them. And that was actually, the field of microlensing kind of started for that reason. Microlensing started as a way to search for black holes as a dark matter candidate. And in the beginning, a lot of their searches were targeted at the Magellanic Clouds. So these were off the plane of the galaxy because they didn't want to see stars and other objects that were part of the Milky Way galaxy. They wanted to search explicitly for primordial black holes. And you would expect those to exist further off the galactic plane than most stars are. But yeah, those early searches, they were able to kind of put some limits on how prominent primordial black holes would be, but they haven't been able to rule them out or confirm them either. Okay, so a couple more projects that we're working on here at Berkeley. These ones I'm not working on myself, but I'm very excited to be able to use them in the future. So one of these is Kappa, the Keck All-Sky Precision Adaptive Optics. This is basically just some improvements that are being built to the adaptive optics system at Keck to make us better able to account for the atmospheric turbulence and get even more precise astrometric measurements in the future. So this will make it easier to measure astrometric shifts of microlensing events and maybe get down to even lower masses that would have been harder to see in the past. And then there's another project that's mostly being led by a grad student in our group, Hannah Bullock. And this is called Curios. It's CubeSats for rapid infrared and optical surveys. They're actually, I think they just recently shipped Curios Pioneer. So this is kind of a CubeSat, which is like a small satellite. That's a lot easier and cheaper to launch than like a Hubble or something like that. And so this is kind of a pilot project, a single satellite going up to start monitoring the sky with this much cheaper telescope than most space telescopes are, but it's got a lot of potential for trying to monitor the whole sky to look for microlensing events, as well as other transient brightening events in the sky, like supernovae that would happen out in other galaxies and things as well. Yeah.
What's the maximum, I guess, aperture size for a CubeSat telescope?
I don't have that number in my head. I know that this telescope in particular is 15 centimeters. This one's actually going up on a CubeSat that's got some other stuff going on with it too. It's very experimental. This project is actually really interesting because they're trying to save a lot of money by using basically just a really nice camera and making some modifications to it to make it safe to go into space without melting. And so it's a very exciting experiment. That means we could potentially do this kind of science a lot cheaper if we figure out how to modify these cameras. But yeah, theoretically, you could get a bit bigger than that on a CubeSat, but I don't know the actual limit. But these aren't huge telescopes. These aren't Hubble scale stuff at all. And then the last thing I have is another really exciting thing in the future of microlensing. If you've ever heard anyone talk about microlensing before, I'm sure they've mentioned Roman because we're all so excited about it. This is the next big NASA mission that's going to launch in space. And it's set to launch currently in October 2026, but their real deadline is May 2027, so it could end up getting pushed back a little bit. And the thing that's really exciting about Roman for microlensing is that it's going to do a photometric microlensing survey in a region just off the galactic plane on the galactic bulge where there's a lot of stars. So we're going to get tons and tons of microlensing events. The main goal of this project actually is to detect exoplanets, but there's a lot of potential with it to study black holes as well. And the really exciting thing about it for black hole science is that this telescope is a lot like Hubble, but it has a much larger field of view. So for all of the photometric microlensing events that it observes, we're also going to get high quality astrometric data with it. So in the past, we've selected candidates from photometric microlensing that we follow up with our very expensive limited astrometric time. But Roman is going to get the astrometry automatically with all of its photometric data. So there's going to be just a ton more science that we can do with that without having to do tons and tons more work selecting and following up candidates.
Where will its orbit be?
L2, it's where JWST is, one of the Lagrange points. Okay, that's all I prepared. I have a few other slides if anyone wants to hear about exoplanets with microlensing too, or we can have time for questions. Yeah.
Can you talk about quasars?
So quasars are basically active galactic nuclei, supermassive black holes, generally in other galaxies. These are supermassive black holes at the center of galaxies that are really active, generally from accretion, like we mentioned, is one of the ways to study black holes. And then when you're looking at other galaxies, including quasars, you can also get gravitational lensing on those scales, but that we don't refer to that as microlensing because it's a very different scale that we're talking about, but you can use gravitational lensing where a galaxy or a cluster of galaxies passes in front of some other galaxy and then lenses it. And you're not really seeing that lensing change over time because things are moving so slowly from our point of view when they're that far away. But you can also study these objects through gravitational lensing on a different scale.
Okay.
I'll get into my brief bit about exoplanets then, since that's one of the big motivations for the Roman mission and something I've also worked on a bit. So we showed this animation before of a microlensing event. We got the Einstein ring, the images moving around it. And so this is what might happen if your lens object or star or whatever has a planet around it. If that planet lies in certain locations around the lens star, it can add an additional lensing effect and cause weird little bumps in your light curve. So this is a way that we can find planets orbiting stars all throughout our galaxy. And microlensing can find planets that it's really hard to detect by any other method because you don't even have to be able to see the lens star. The lens star doesn't have to be bright. It can be a really low mass star really far away that you wouldn't be able to see otherwise, but you can see it through microlensing. So this is a way to study what planets are like in very different parts of our galaxy, as well as planets that are further from their planets than we can, or sorry, further from their host stars than we can often see. So these are typically planets kind of like Jupiter and Saturn, more distant, cold planets, generally at or beyond Earth's orbital distance. And so this is a particularly fun microlensing event. I like to put this event up whenever I have a chance to, because this is the microlensing event that made me decide to become an astronomer. And so this was the first microlensing detection of a multi-planet system. So they had this super wacky light curve with all of these weird things happening. This is a weird effect of gravitational lensing when there's multiple lenses that we call caustics. The math is very complicated, but basically you get really, really crazy light curves when you get passage of a source star through a caustic structure. And so this was a really, really exciting discovery of a multi-planet system that was a lot like Jupiter and Saturn around its own host star out in the galaxy. Yeah.
So because there's 5 little bumps, does that mean there's 5 planets in the system?
So it's 2 planets, but when you've got 3 objects in the lens like that, instead of being like the simple Einstein range structure that you get for lensing when there's a single lens, you get these really weird caustic structures. So what's happening is that it's either closely approaching the caustic structure or passing through it 5 different times. So it has 5 encounters with the weird lens structure.
Did you say caustic?
Caustic.
Caustic. C-O-S-T-I.
C-A-U-S-T-I-C.
Oh.
Yeah.
What was the limb?
It was
a black hole?
It was a star.
Oh.
A star with 2 planets.
Yeah.
Does the microlensing affect the wavelengths of the light? So for exoplanets, you measure the wavelengths to determine like the
Like transmission spectroscopy.
Yeah.
Does
it alter it? And if so, can you account for it?
Microlensing is wavelength agnostic. It doesn't do anything as a function of wavelength. And actually, when we're talking about the lens, like lensing planets, the planets are orbiting the lens star, not the source star. So we're not necessarily seeing any light coming from them. So we're really only seeing their gravity, and we're not really able to learn anything about their atmospheres. We can usually measure their mass and their distance from their host star, and that's all the information we get from this.
Just kind of random factoid. So what's the closest object that has exhibited lensing?
I don't know if I know that off the top of my head.
It's not Jupiter, right?
Oh, I mean, this wouldn't really be in the regime we would call microlensing, but we've observed the sun lensing background stars during a solar eclipse. So that would be the closest one, yeah.
Sorry. It's been so long.
Yeah. Sometimes I forget about that one. And so my last slide here is just about the future of planetary microlensing with Roman. So as I mentioned, most other exoplanet detection methods find stars that are pretty close into find planets that are pretty close into their host stars. So this axis is distance of the planet from its host star, and this axis is the mass of the planet. So Kepler was a transiting survey. It detected planets by them passing in front of their star and blocking their light temporarily. And so the transit method and some other methods that are shown in black dots all kind of find planets in this region. So primarily, decent sized mass up to really high mass planets that are pretty close into their host stars. Microlensing, especially with the Roman mission, is going to find planets like the simulated planets that are shown in blue here. So these are simulated planets, but it's the kind of thing we expect to find with Roman. We're able to find stars a lot more distant from their host stars and along a wide range of masses. So you can see where the solar system planets fit into this structure here. And when we're looking at Jupiter, Saturn, Uranus, Neptune, and even Earth, most of these planets are best covered by the microlensing method in a way that a lot of other types of exoplanet searches are not able to find them. And then we can also detect free-floating planets not attached to a star at all. And there's generally no other way that you would expect to find those because they're far too dim.
Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 planets marked there. Doesn't our system have 8 if you don't count Pluto and 9 if you do? What's the 10th dot?
I think this might be the moon.
Oh.
And what's my big planet get classified as non-planet?
2006, I think.
Okay, that was longer ago than I thought. They might have just put it on the spot for fun. I'm not sure. Actually, I don't think they did, just distance-wise, though. There's nothing past Uranus and Neptune, so they didn't put Pluto on it. Okay, I think we're perfectly about at time then.